Howdy! Welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 10.1, Correlation. Here in this lecture, we're going to start out by looking at some definitions and requirements for correlation. This should be a review since we talked about correlation a little bit back in Chapter 2. So we're going through these topics. You may get the sense of familiarity with some of this, and that's because we discussed it before in Chapter 2. But we're going to go over it again because it's been a while since we were in Chapter 2. So we're going to refresh our memory a little bit by going over definitions, requirements, talk about scatter plots, the linear correlation coefficient, its properties, and how to interpret it. But then we're going to get into the concept of explained variation, which we didn't touch in Chapter 2. And then we're also going to talk about hypothesis testing with correlation. So how do we form a hypothesis and how do we test it? So you're going to see the linear correlation coefficient symbolized with the lowercase letter r. That's what your author likes to use. But other sources use a capital letter R to represent the linear correlation coefficient. I personally like the capital letter R, but we're going to go with what your author says here so you don't get confused when you compare this with your homework assignments in the textbook. So the little letter r is what we're using to represent the linear correlation coefficient. It measures how well paired sample data fit a straight line pattern when you plot them on a graph. Now, sometimes when you use paired sample data and you find your value of r, you can then conclude whether there is a linear correlation between the two variables. Oftentimes we'll use technology to do this because calculating r the old school way by hand is pretty involved, but we will get into that a little bit to show you what it actually takes. And then you'll have an increased sense of gratitude for the fact that we live in the 21st century and we have access to technology that lets it calculate it for us. Now, keep in mind that when we're looking for correlation between two sets of variables, which we're going to be using paired sample data for, that we're only going to be considering linear relationships. So if the points, when you graph them, approximate a different type of pattern, you could actually make a model based on that different type of pattern with that data. However, we're only going to start with the linear relationships, so that's all we're going to look at. So we're going to look at linear correlation. Now, when we get later on in the chapter, we'll talk about nonlinear relationships. So nonlinear correlation, nonlinear regression, how to make models based on nonlinear types of curves. We'll get into that later in the chapter. But for right now, we're just going to set the stage talking about linear correlation. And as mentioned previously, we can actually make hypothesis tests to evaluate whether paired sample data is linearly correlated. We're going to talk about that as well in this lecture. Start off with, let's review some definitions. So a correlation exists between two variables when the values of one are somehow associated with the values of the other in some way. There's some relationship between the two. Now, just because there's a relationship between two variables does not mean that that relationship is one of cause and effect. It could be that the two variables you're looking at are related to each other through a third variable that you're not looking at. So it doesn't stand to reason that just because there's a relationship between two variables that the relationship is cause and effect. Making that connection is a logical fallacy, so don't go there. Now, we have what's called a linear correlation when two variables are correlated to each other and the plotted points of paired data result in a pattern that can be approximated by a straight line. A nonlinear correlation, on the other hand, exists when you have correlation between two variables, but the plotted points of paired data result in a pattern that's approximated by something other than a straight line. So it's a parabola, or it's a sinusoidal curve, or it's an exponential function, or it could be something else entirely. But it's not a straight line pattern. That's nonlinear correlation. Again, what we're going to focus on initially is linear correlation. We'll address nonlinear correlation in a future lection in this chapter. So, evaluating linear correlation, we need to calculate what's called the linear correlation coefficient. This measures the strength of the linear relationship between paired values in a sample. Of course, there's some requirements with our methodology, as there always are, because we're making certain assumptions when we use our methodology. So, for paired sets of data, we have to meet certain requirements in order to conclude that they're linearly correlated. First, we need to know that the sample of paired data is a simple random sample of quantitative data. Note that this will not work with categorical data, so it has to be quantitative. We also need to see a scatter plot of the data showing the points approximate a straight line pattern. This is easy enough to do, but when you make a scatter plot, you need to be looking for outliers, and any outliers that are known to be quote-unquote errors must be removed. Outliers have significant influence over your linear correlation coefficient, as we'll examine a little bit later. They have a huge effect in also creating the regression models that are coming out of the correlation analysis. So we really want to make sure that the outliers are removed as much as possible. Oftentimes, the effects of any outliers should be considered when calculating R with and without the outliers included. And so you can't just take data points out of your data set. You need to have justification for removing data points from your data set. So, for example, this one data point that's an outlier, for example, it represents, say, a field unit that your customers have been operating for, say, 10 years. But all the other data points in your data set were from field units that customers were using for, say, 5 years or less. Well, that 10-year data point is going to be an outlier. And so you can justify removing it from your data set because it really is an oddball. It doesn't represent the way your customers are using your field units. So you could take that out of your data set and then make your linear regression model with the rest of the data points. But you can't just remove the data point. You have to have some rationale, some justification for removing it. Oftentimes, there may be instances where you want to leave an outlier in a data set. And again, you have to look at the context of the specific situation in order to know, are we going to leave it in or are we going to leave it out? Very often what you end up doing is making a model both ways. So you're going to look at it with the data point in, you're going to look at it with the data point out, and then you're going to compare the two and say, which is the more realistic model? Which produces more realistic predictions based on my data set? And that's oftentimes a key question that you're going to ask in determining whether you leave an outlier in or take an outlier out. One of the key points, one of the key tools that we use in determining whether or not we leave an outlier in or take it out is a scatter plot. And in fact, when we have paired sample data and we're looking to make a model with it, one of the very first things we do is we make a scatter plot with it, because the scatter plot shows us the relationship of the data points to each other. If there's any obvious pattern that we can use to form the basis of our model, it's going to become apparent in the scatter plot. So we're going to see what relationship there is, if anything, between two variables by constructing a scatter plot. For this reason, it's one of the first things we do when we're performing a regression analysis to make a model. So here on the screen we have different scatter plots of data points, and we can see that there's different patterns represented by each one. If you look at each of the plots and read them like a book from left to right, this will help you to notice any trends that are in the data. So what you end up doing as you're going from left to right, imagine drawing a line of best fit through your data points. So if we look, for example, at this first data set labeled strong positive correlation in the upper left corner of the 6 that we see here in the center of the screen. So if we draw a line that seemed to best fit the data points, it would look something like this. Notice our line of best fit doesn't go through every single data point, but it seems to fit all of the data reasonably well and represents the general trend or pattern that we see in the data. This is our line of best fit. Now, we say that we have strong correlation when the data points lie close to this line of best fit. As you see here in this example of strong positive correlation, the line of best fit, again, doesn't go through all the points, but all the data points in the data set lie reasonably close to this line of best fit. Therefore, we say that these data have strong positive correlation. A moderate or weak correlation would exist when the data points are more spread out. So you can see that we still resemble that trend of a straight line as we go from left to right, but the data points aren't as close to that line of best fit as we saw with the example of strong positive correlation. So the farther away those data points get from your line of best fit, the less correlation you're going to have. Note that these first two examples we looked at, we have positive correlation. All that means is that the line of best fit, it has a positive slope. So as you go from left to right, reading like you do a book, the line of best fit goes up. If we look at the two examples below those first two that we looked at, we have negative correlation. That's because in these instances, the line of best fit, as you go from left to right, goes down. So these lines of best fit have a negative slope, whereas the lines up above for positive correlation have a positive slope. Sometimes the line of best fit is not a straight line. This is an example of what we would call nonlinear correlation. So again, the stronger the correlation, the more those data points are going to adhere to that line of best fit. In this instance, the line of best fit is not straight line, it's curvilinear. And so we have a nonlinear relationship. But the distance that those data points have from the line determines the strength of the correlation. So here we would say we have a reasonably moderate correlation because some of these data points are really close to the line and other data points are farther removed from it. Then finally, we can have a data set where the data points have no correlation. This means that there's no single line of best fit for the data, and you see a characteristic shotgun appearance with this data set in a scatter plot. So, as you can see here, one of the first reasons why we make a scatter plot is because we get a reasonable idea of whether a relationship between the two variables even exists. Scatter plots are really easy to make in StatCrunch. We've done this before back in Chapter 2, but just to review, let's go over the steps for making scatter plots in StatCrunch. So first, make sure your data is in StatCrunch, and then go to Graph Scatter Plot. In the options window that appears, you're going to see a lot of bells and whistles, but you're not going to need most of these for your assignment. So just accept the default values for all of these options. You want to make sure you identify the columns that you're going to use for your data. So you do that right at the top of the window. Tell it where to find the X variables and the Y variables, and then you go to the bottom and press Compute. And then you get a scatter plot that shows up as your results window. Now, keep in mind, some of your homework problems may try to mess with you by adjusting the scales on the graph. You've got a couple of options to get around this when you're looking for the matching scatter plot. So the first option is you can put your cursor on the edge of the window and then drag the window to change the size of the plot area. Second, there's these three bars that you see in the lower left-hand corner. If you select those three bars, so you left-click it with your mouse, and then you're going to go into a menu where you can select the axis that you want, the x-axis or the y-axis, and then an options window will appear where you can enter in new values for your axis. So you can tell it where to start, where to end up, and you can change the values to match what you see in the answer options for your assignment. Let's take a look at an example to illustrate. So for the data set in the table above, select the correct scatter plot below. So we have 4 scatter plots that were given, and we're asked to select the one that matches the data set provided. So first we're going to put this data in StatCrunch, and then we'll go to Graph Scatter Plot. We pick the columns that tell us what our X and Y is, and then we press Compute. Now, what happens if you don't know which data column goes with the X and which go with the Y? Well, that's a very good question. And for most problems, you're going to be told which is which, so you don't have to worry about it. However, it's highly possible that, the rare event is that you're not told, and so in that instance, you're always going to compare values on each axis with the values in your data set. So in this instance, for example, let's say we didn't know what the X and the Y were. Well, look at your values for X. They're all in the single-digit range, so they're between, yes, like the lowest one is a little more than 4, and the biggest one looks to be this 7.6. So everything's between 4 and 8. So we're all in like single-digit category on a number line. But now look at your Y values. See how we're all triple digits? Everything's centered around, say, 140 to 160. So you've got 2 completely different ranges for your X and your Y. So you could look at each of these different options and say, okay, well, obviously, answer option D is not going to be the answer, because look at the values for Y. They're so small. They're much smaller than the values we have here in our data set. So this is obviously not going to be the right answer. So right off the bat, we can get rid of answer option D. You can also take a look at the values that are listed here in the different data tables and look and see, well, is there something here that's out of sync? For example, here in answer option A, notice we have a value here at 182, and the minimum value is around 174. So that's well outside the range of the data values that we have for Y in our data set here. So this is obviously not going to be the answer we're looking for. So you can get around not knowing what the X and the Y is. Just compare the values in your given data set with the values that they give on the axes. When we do actually make the scatter plot, we get something that looks like this. And so comparing this with the patterns that we see in these 4 options, obviously the one we're going to pick is answer option B. Let's talk for a moment about the linear correlation coefficient. I mentioned earlier that we're going to talk about the old school calculation method. Well, here it is. This is the equation for calculating the linear correlation coefficient. As you can see, it's pretty calculation intensive. Having to calculate each of these different variables by hand, wow, it was a nightmare. And I can remember doing this by hand when I took this class in college, and yeah, it was just not a very pleasant experience. I'm very thankful that I'm now in the 21st century where I have access to all kinds of computer software that can do this for me. But back in the day, oh my, it was pretty painful having to calculate this out. So let's go over each one of the variables here in the equation so that we understand where the linear correlation coefficient is coming from. So we're not just pressing buttons on the computer, but we actually understand what's going on in the background in that split second it takes for the computer to actually run this calculation. Notice we have N, which is the number of pairs in your sample data. This is our sample size, and we've seen this variable before. It appears in 3 different parts of our equation. The sum of xy means that you take each x value, multiply it by its corresponding y value, and then you add all those products together. The sum of the x's means you take all the x values and add them together. The sum of the y means you add all the y values together. The sum of the x squared means you square each x value and then add all of those squared numbers together. The sum of the x quantity squared means you add all the x's together and then square that number. So very different whether you're looking at the sum of the x squareds or the sum of the x quantity squared. We have the same thing for the y. So we have the sum of the y squareds meaning you take all the y values, square each of them, and then add those squares together. Or you could have the sum of the y quantity squared, which means you add all the y values together and then square that sum. Knowing how we calculate the value of r, we can deduce certain properties that r is going to have. The first is that r cannot be less than -1 or more than +1. So it's bounded within this range between 1 and -1. Now, all values of either variable are converted to a different scale, then the value of r does not change. So we can perform data transformations on our data set, but that's not going to necessarily change the value of r. The value of r is not affected by which variable you choose to be x and y. So you could say, okay, I'm going to do a linear correlation on this set of paired data, and you're going to go into StatCrunch, for example, and say, okay, this is my x, this is my y, and then get a linear correlation coefficient from that. If you go back to your options window and then swap the x and the y, and then press compute, you'll see that you get the exact same value for r. This is because it's not affected by which set is x and which is y. So the value of r is going to change. You can interchange those two all day long. You're going to get the same linear correlation coefficient out. The value of r measures the strength of a linear relationship. And you can see that with the scale at the bottom of the screen. So the closer you get to 0, the more you have no correlation between your data values. Between the x and the y values of your data values. The more you get to the edges of the range, so the closer you get to 1 or -1, the more your data set is going to be correlated. Now, all the negative sign means is that you have negative correlation. So that line of best fit is going to have a negative slope, which means as you go from left to right on your graph, the line will go down. Positive value for r simply means that your line of best fit has a positive slope to it. So that line of best fit, as you go from left to right, is going to go up. And that's all the positive and negative means on it. Other than that, the closer you are to the edge, the more you have correlation. The closer you are to the middle of that range, the 0, that's where you have no correlation. Keep in mind, the value of r is very sensitive to outliers. We've been mentioning this. We're going to keep mentioning this. I'll show you here in a moment that this is actually true, and I'll show you the actual impact that one outlier can make in your data set. We'll look at that momentarily. First, let's look at how we actually interpret our value for r. So we have two ways to determine whether our linear correlation coefficient is indicating a linear correlation between two variables. First, we can use the table that you see on the right side of the screen. This is the same table that's in the insert for your textbook. I believe it's labeled table A6. So, using this table, if we have this absolute value of r that we calculate exceeding the corresponding value from the table, then we have a linear correlation. Conversely, if we're equal to or less than the corresponding value in the table, then we do not have enough evidence to support the conclusion of a linear correlation. The other way to determine whether a linear correlation exists is to use a p-value. So we can take a p-value and compare it with our significance level, as we've done previously. So if the p-value, again, can fit inside that alpha area, we conclude we do have sufficient evidence to support the conclusion of linear correlation. And where the p-value is greater than the area of that alpha, then we do not have sufficient evidence to support the conclusion of linear correlation. Know that the methods in this section apply to linear correlation, so we're not going to use them with nonlinear correlation, only with linear correlation. So if you conclude that there isn't a linear correlation, there may still be an association between the two sets of the x and the y of your data values. There may be a nonlinear relationship between the two. So don't jump to conclusions and think, oh, well, if there's no linear correlation, then there's just no relationship between these data. No, that's not the way to do it. You don't want to jump to conclusions. There may be a nonlinear relationship at work, and you'll need to investigate that to understand whether or not that's even an option that's in play. Don't just go assuming that because there's no linear correlation, there's no correlation at all. Let's look at an example to illustrate these concepts. So we're going to look at shoeprint length and height. And I believe we looked at this back in Chapter 2, but it provides us with a good example of looking at linear correlation. So let's go back to this example and use it. So we have a data set here from 10 randomly selected subjects where we measured the length of their shoe print in centimeters and we measured their height in centimeters. So now we're asked, what is the value of the correlation coefficient R, and are shoe print length and height linearly correlated at the 5% significance level? First, before we use any methodology, we need to check that our requirements are met. So, sample paired data is a simple random sample of quantitative data. So we got that first requirement out of the way. And yes, that's what we have. We don't have any categorical data. We have a simple random sample. So we've got that first requirement. Next, we need to know that a scatter plot shows the data points approximating a straight line pattern. So here's a scatter plot of our data. And while it's not necessarily the straightest of lines, you can see the general trend in the data as you go from left to right across the plot. The general trend in the data is one of increasing value. So we could say that, yeah, the scatter plot here shows that there could be some correlation here. The wide band, which is basically the band that we would actually list our data through, is actually pretty wide here. So there may be no more than a moderate linear correlation, but a correlation nonetheless. So if you imagine like two dashed lines representing the edges of this band that I'm speaking, notice that all the data points lie within that band, and that the general trend of the band is continually upward as we go from left to right. So because this band is pretty wide, we're going to see no more than a moderate linear correlation if we see a linear correlation at all. Here's our line of best fit, which would be in the center of that band. And so you can see that, yeah, it generally follows that trend. And so this is the value of the scatter plots. We can kind of get a visual look and see if there's a potential relationship between these two variables before we do any sort of analysis. Outliers known to be quote-unquote errors must be removed. So here we see that all of our data is within those bands that we saw earlier when we were evaluating the scatter plot. So there's no real outliers here. Everything is more or less together. So now we've seen that we have our requirements met. Let's go ahead and calculate and interpret the value of R. Using StatCrunch, we find that we have a linear correlation coefficient of 0.847. We get that from our results window when we do the linear regression analysis. So up here at the top, we have listed our value for R. This is 0.847 when you round to 3 decimal places. To determine whether a linear correlation exists, we can use our critical R value table. So here's our critical value table that we have for our linear correlation coefficient. We're testing at the 5% significance level. So we're going to use that center column there to get our critical R value. It's labeled at the top, alpha equals 0.5. So we're going to use this column to find our value. Now, from the table, we find the critical value for R for this significance level is 0.632. How do we know which one of these values to select? Well, we look for our sample size. We have 10 randomly selected subjects that provided value, so therefore the corresponding critical value for R is 0.632. Now we compare the value for R we calculated with that critical R value, and we find that we're greater than the critical R value. So because we're greater than that critical R value, we conclude shoe print length and height are linearly correlated. This R value becomes a sort of quote-unquote test statistic that we compare with our critical value to then make a conclusion whether we have sufficient evidence to support a claim of linear correlation, or we fail to reject H naught, in which case we have insufficient evidence to support a claim of linear correlation. Alternatively, we can use the p-value and compare it with our significance level. Notice the p-value we're going to use is here in our results window in StatCrunch, 0.002. You want to take the value right here from your parameter estimates table. It's this last value listed here. This is the p-value you want to use. I know the p-value listed there in the ANOVA table is the same, but there will be instances, especially when we start adding more variables into our linear regression model, where those p-values are not going to be the same. So you want to get in the habit of taking your p-value right here from your parameter estimates table. Because our p-value of 0.002 is less than our significance level of alpha of 0.05, 5%, then we can conclude that shoeprint length and height are linearly correlated. The area represented by the p-value can fit inside the area represented by alpha. Therefore, we're in the rejection region, we reject H naught, and we conclude shoeprint length and height are linearly correlated. Let's talk for a moment about a concept called explained variation. So if we take our linear correlation coefficient and we square it so that it becomes r squared, then this value becomes the representation of the proportion of the variation in y explained by the linear relationship between x and y. So there's variation in the values for y in our data set. Typically, your y values are not going to be the same, so there's some variation there. How much of that variation is explained by the linear relationship that exists between x and y? That's what we get when we calculate explained deviation. Now, graphically, you can see in the chart there on the top right of your screen, there's explained deviation and unexplained deviation. An explained deviation or explained variation is simply the distance between your regression line and the mean value of y for any particular data point. So that's the explained part, and the unexplained portion is the distance from the regression line up to the data point that we're interested in. So there's an unexplained portion and an explained portion. The unexplained portion comes from statistical error, which we'll get into later, and then the explained portion comes from the linear relationship. That's why we call it explained and unexplained. There are errors in the statistical calculations that are creating this unexplained deviation. We don't know exactly what those errors are or where they are. That's why it's called unexplained. The explained variation comes from the linear relationship. We know where this variation comes from. It comes from the linear relationship between x and y. Therefore, we can explain this portion of the variation, and that's why this is called explained variation. Now, previously, for our example of shoe length and height, we found that our linear correlation coefficient was 0.847. So, if we have 0.847 for r, we square that to get r squared. That gives us a value of 0.717. You don't have to do that manually. This will show up in your results window in StatCrunch. It's right underneath where you see listed the linear correlation coefficient, that value 0.847. Right underneath that will be the value for r squared. That's 0.717. So it calculates it for you. So here in the results window of StatCrunch, you can see right here underneath the linear correlation coefficient is listed the value for r squared, 0.717. So you don't have to do any calculation. StatCrunch will do that for you. What this value means is that there's 71.7% of the variation in height, this is our y value, variation in height that can be explained by the linear relationship between our x, lengths of shoe prints, and y, which is heights. So the linear relationship between lengths and shoe print length and height explains the variation of 71.7% of the variation in the height. Let's relate this back to linear correlation. So for each of the examples that we're listing below, determine first whether a linear correlation exists, and then second, what percentage of the variation in y is explained by the linear relationship. So the first example we have here, sample size of 12, significance level of 5%, and a linear correlation coefficient of 0.654. First, determine whether a linear correlation exists. Well, what we're going to do first is determine, this is our R value that we calculated. We have to compare it with a critical R value. So we go to our table here of critical R values, and we look to see, okay, so significance level of 5% and sample size of 12. So that's going to lead us to this critical value here, 0.576. And since our R value is greater than 0.576, we're going to conclude there is a linear relationship. So yes, this is our critical R value that we see here. There is a relationship because we're greater than that critical value. So the answer to the first question is yes. If we square our R value, we then get 0.428. This tells us that 42.8% of the variation in y is explained by the linear relationship. Let's look at another example. So sample size of 30 and significance level of 1%. Our R value is 0.453. So, do we have a linear correlation? And what percent of the variation in y is explained by the linear relationship, assuming there is one? I'll give you a moment to determine your answer. Okay, I hope you said there's no linear relationship here because our critical value, we do 1% significance level for 30 samples, we get a critical value of 0.463. So notice that 0.543 is just less than that. So because we're less than our critical value, there is not sufficient evidence to conclude a linear relationship exists, and so we have to say no. And that means that the answer to the second part is 0. 0% of the variation of y is explained by the linear relationship because there is no linear relationship. We don't have sufficient evidence to conclude there is one. So we just assume there isn't one, and therefore the percent of variation of y explained by the linear relationship is 0. Let's look at another example. Suppose we have a sample size of 17, testing again at the 1% significance level, and we find we have a linear correlation coefficient of 0.877. Determine whether a linear correlation exists and what percent in the variation of y is explained by the linear relationship. I'll give you a moment to determine your answer. Well, I hope you said there is a linear relationship here. So critical value for 1% significance level, sample size of 17, 0.606. We compare that with our R value. 0.877 is greater than 0.606. Therefore, we do have a linear relationship between this set of variables. The percent of variation explained in y, we just take our R value and we square it, and we get 0.769. So 76.9% of the variation in y is explained by the linear relationship. Here's another example. Sample size of 7 with a significance level of 5%. Linear correlation coefficient 0.897. Do we have a linear correlation here? And if so, what percent of the variation in y is explained by the linear relationship? Again, I'll give you a moment to determine. So I hope you said that there is a linear correlation here because our critical value is 0.754. So 5% significance level with a sample size of 7 gives us a critical value 0.754. That is less than our calculated R value of 897. So since we're over the critical value, we do conclude that there is sufficient evidence to support the claim of linear correlation. We then take our R value and square it. 0.897 squared gives us 0.805. That means 80.5% of the variation in Y is explained by the linear relationship. Let's look at one more example. So here we have a sample size of 25, significance level of 5%. Our R value that we calculate is 0.396. Again, I'll give you a moment to determine your answer to the same questions. So here we do not have a linear correlation. So looking at our critical value for a sample size of 25 with a significance level of 5%, that gives us a critical R value of 0.396. So 0.396, that's the same value that we calculated for R. We're right there on the borderline. So you can't be on the fence and conclude linear correlation. You have to be over the fence. So since we're not greater than our critical R value, we conclude there's not sufficient evidence to support a conclusion of linear correlation. And because there's no linear correlation, 0% of the variation in Y is explained by the linear relationship because there is no linear relationship. Let's look at one final example. Sample size of 2 with a significance level of 1% and an R value of 1. Do we have a linear correlation? And if so, what percent of the variation in Y is explained by the linear relationship? Again, I'll give you a moment to determine your answer. So here in this instance, we do have a linear relationship. I mean, an R value of 1 is perfect positive correlation. You can't get any more correlated than this. So you've got a correlation coefficient of 1, but you're really not going to expect anything else when you've only got 2 data points. I mean, you've got 2 data points to make your line. So of course you're going to have a straight line that goes directly through each of those points. Of course you're going to have the best linear correlation coefficient you could possibly have. There's no way that there could be any deviation of either of those 2 data points from your line of best fit, because you need both of those lines to make your line of best fit. So because you have this perfect linear correlation, the percent of variation in Y explained by the linear relationship is 100%. Let's look at some common errors that are made when considering linear correlation. So first we have the error of causation. There are some who wrongly conclude that just because you have a relationship between 2 variables, it means that one causes the other. I've said this before, I'll say it again, I never get tired of saying it, that just because you have a relationship between 2 variables, it doesn't mean that relationship is one of cause and effect. Correlation never implies causality. Correlation simply means that both variables tend to occur together. There is a relationship there. It doesn't necessarily mean that it's one of cause and effect. As I've said before, it may be that both your variables that have this relationship, the relationship is because they're related to the same third variable that you're not looking at. Another common error that's made is the use of averages. So some use averages instead of individual values when calculating R. This is a common error, and it's erroneous because of the way that R is calculated. Think about it. If we use averages based on the way that we're calculating R according to that nasty long equation we looked at previously, what that ends up doing is suppressing individual variation, and it can artificially inflate the value of R. So you get a calculated value for R that's higher than what it really should be. What that means is when you're going to compare with your critical R value, you may be concluding you have sufficient evidence to support a conclusion of linear correlation when in fact you may not. So don't be using averages to inflate your value of R. You're going to suppress the individual variation in your data points and get something that's actually you're going to get something that's actually not what it actually should be. So always use individual values when evaluating correlation and not averages. They're trying to simplify that calculation, but in so doing, they obscure the usefulness of it. A third type of common error that's seen involves linearity. So there are those who say, well, you know what? If there's not a linear relationship, then there just isn't one. And I mentioned before that's erroneous. There may be a different type of relationship between the variables. So not every relationship in the world is linear. I mean, yes, we would love every relationship in the world to be linear, because if every relationship in the world were linear, then we could model everything with a straight line, and straight line models are the simplest types of models you can make. They're very easy to manipulate, very easy to interpret, and they're very easy to use. So you want everything to be linear. But unfortunately, that's not the world we live in. The real world has many things that are related in non-linear ways. And so you want to be open to the possibility that, okay, so you've done your test and you found that there's no linear relationship between your variables. That may not mean that there's no relationship. There may be a relationship, it's just non-linear. So if you find that what you're looking for is not in one place, go looking for it somewhere else. So this is one of the reasons why we make our scatter plot, because you know what? That scatter plot can tell us, say, look, okay, there may be a non-linear relationship at work here. What type of non-linear relationship could we be looking for? Sometimes our scatter plot can give us a clue as to what we're looking for, so that we can then hone in on the answer we're looking for much faster. Again, I'm going to say it. Just like apples are not oranges, correlation is not causality. Just because two variables have a relationship to each other, it doesn't mean that that relationship is one of cause and effect. We're kind of using some hypothesis testing verbiage as we've described interpreting our value for R. Let's actually go into using the linear correlation coefficient for hypothesis testing. Much of what we've seen before is going to apply here, so many of the same conventions are here. Hypothesis tests for linear correlation can be one-tailed or two-tailed. If the claim is simply one of linear correlation, we have a two-tailed test. This is typically what you're going to see when you're doing a hypothesis test on linear correlation. You typically see a two-tailed test, where your null hypothesis says your linear correlation coefficient for the population will equal 0, and the alternative hypothesis is that it does not equal 0. However, if the claim is one of positive or negative linear correlation, so we're making the claim of linear correlation, but it's on a specific side of 0. We're saying the correlation is positive or the correlation is negative. Well, then we're not looking at both sides of that range of R. We're only looking at one side, and therefore we have a one-tailed hypothesis test. Negative linear correlation will be a left-tailed test. Positive linear correlation will be a right-tailed test. Now, there is some special notation that we use with hypothesis testing for linear correlation. First, as always, little n represents the number of pairs of sample data. This is our sample size. Little letter r is going to represent the linear correlation coefficient for a sample of paired data. The lowercase Greek letter rho will represent the linear correlation coefficient for a population of paired data. Typically, we see the lowercase letter representing the sample and the uppercase letter representing the population. In this case, we're not going to use a capital letter R to represent the population linear correlation coefficient because, again, many sources use the capital letter R to represent the sample linear correlation coefficient. So in order to avoid confusion, I think what we're doing here is using that lowercase letter r for the sample linear correlation coefficient and a lowercase Greek letter rho, which is the Greek equivalent for the lowercase letter r, as the population linear correlation coefficient. So we have the same three requirements for establishing linear correlation with hypothesis testing that we've seen all along. So we need to make sure those are met. We also form the hypotheses just as we've done previously. So typically you're going to see a two-tailed hypothesis test. You're just looking for some correlation. It's not specified whether that correlation is positive or negative. It's just any correlation. So in that case, you have a two-tailed hypothesis test. The null hypothesis, as always, will be a statement of equality. So we take our population parameter, which is the population linear correlation coefficient rho, and we set that equal to 0. The alternative is then going to be that rho is not equal to 0. So rho equal to 0 means that there is no linear correlation. Because again, remember the scale that we had before when we learned about interpreting values for r. 0 is right in the middle of that range of possible r values. And when you have an r value of 0, you have no correlation between your data points. So you're in this region of the range if the null hypothesis is true. If, however, we fail to reject the null hypothesis, that means it's possible that the null hypothesis could be 0. If the null hypothesis is not 0, then that means that there is some linear relationship. So we're looking at, say, positive correlation on one side or negative correlation on the other. And so we're looking at the ends of the range. And so this is where we get the two-tailed hypothesis test from, because we're looking at each side of the range, just like we looked at each of two tails in a distribution when we ran a two-tailed hypothesis test. Now, the linear correlation coefficient R can be used as a sort of test statistic for hypothesis testing. We then evaluate the test using tabulated critical R values as we saw previously. So, if the absolute value of R that we calculate is greater than the critical value from the table, we reject the null hypothesis and conclude there is sufficient evidence to support the claim of linear correlation. We reject the null hypothesis because if the R value we get is greater than the critical value from the table, then clearly R is not going to be equal to 0 for the population. So that means that we're in one of these two tail regions where we have some moderate amount of correlation between our sample variables. If we're looking at an absolute R value that is less than or equal to critical value from the table, we fail to reject H0 because we don't have enough evidence to prove that it's not 0. Therefore, it really could be 0, and so we want to conclude, hey, we may be in this center region here where there is no correlation. Therefore, we conclude there's not sufficient evidence to support the claim of linear correlation. When you're calculating your test statistic, up till now we've been using as a sort of quote-unquote test statistic the linear correlation coefficient that we calculate. The true test statistic for a hypothesis test on linear correlation is a t-score with n-2 degrees of freedom. Notice this is a different calculation for degrees of freedom. Notice that previously we always calculate degrees of freedom as 1 less than the sample size. Here we're using 2 less than the sample size. So our test statistic, calculated according to this formula, we take our linear correlation coefficient, and then we divide it by this mess here, which is the square root of 1 minus r squared divided by the sample size minus 2. So this is our degrees of freedom, n minus 2. We then use this test statistic with our t-distribution to find the p-value. So here we have, if we have, for example, a sample size of 12, then we have 10 degrees of freedom, and therefore we're going to put in here, notice we're using half of our alpha value. So remember, two-tailed test, only half of alpha is in one of the tails, so I put half the alpha in here. So half of 5% is 2.5%. Calculate out, press compute, and then I calculate out the critical value here. So this is the critical value that I can then, this is, excuse me, the test statistic that I can then use to find. This is the critical value I'll then compare with my test statistic. So we either use that or the p-value. Again, reject H0 if we're inside the critical region. Fail to reject H0 if we're outside the critical region. Now, for the homework problems in this section, there's a single option StatCrunch that provides most of what you need. So if you go to Stat, Regression, Simple Linear, that will give you most of what you need. So here in the options window, after you press that, notice that most of the defaults you just leave as is. You're going to select the columns for X and Y, of course. You're going to be able to do that first. And then once you do that, you've got everything you need for linear correlation. So go ahead and just press compute. Then you get this lovely little results window, and you can read your value straight off of it. So here's our value for R, linear regression correlation coefficient. Notice right below that we have the value for R squared. So this gives us the percentage of variation in Y that's explained by the linear relationship. We have a p-value listed here, again in the parameter estimates table, not the ANOVA table. And then the test statistic, the true test statistic, right next to it. Notice that before we're using our R value for test statistic 0.04585, so on and so forth. The true test statistic here in this case is 0.091799. We can also make scatter plots in StatCrunch, which we looked at previously. But when I'm working these problems with linear regression, I don't make a separate graph for the scatter plot. When I'm working these problems, I go straight to the linear regression analysis. Now, you may be wondering, why is he going to the linear regression analysis when he said earlier one of the first things we do is make a scatter plot? Well, the reason I'm doing that is because when you do that regression analysis to look for correlation in StatCrunch, you're actually looking at a results window that has 2 pages. And on the second page, you see a scatter plot already made for you. So you don't have to go through 2 separate menu options to get the scatter plot. Just go straight into that linear regression to test for correlation, and you can get the scatter plot that you're looking for. So here's an example results window. This is the same one that we saw on the previous slide. Notice up above the 1 of 2 next to the options button. This says that there's more to see. There's actually 2 pages to your results window. So if you press this little arrow down in the bottom right-hand corner of your results window, then your results window will change to the second page. Notice now we have 2 of 2 up at the top. And look, we've got this wonderful little scatter plot along with a line of best fit going through the scatter plot. So I never make a separate scatter plot when I'm working in StatCrunch. I go straight to the linear regression. And then if I want to look at my scatter plot, I just use that arrow down at the bottom of the results window to look at my scatter plot. I don't have to do anything extra. Lazy engineers rule the day. Let's go back to our example of Shoeprint length and height. So we can use the data set from our previous example to evaluate the claim, this is a hypothesis test, that Shoeprint length is linearly correlated with height. Now, because there's no indication here of positive linear correlation or negative linear correlation, the claim is simply about linear correlation in general. So it's any linear correlation. What we have is a two-tailed hypothesis test. We're going to write our hypothesis first by expressing the claim symbolically. So our claim is that our two variables are linearly correlated. That means they could be positively correlated or negatively correlated. So it could be greater than 0 or less than 0. So we just write that symbolically as rho is not equal to 0. The null hypothesis, by definition, is a statement of equality. So here I'm going to make my null hypothesis rho equal to 0. The alternative hypothesis generally reflects the claim. We see that true in this case, where rho is not equal to 0. Notice here we have an interesting setup. So here we actually have a match between the claim and our alternative hypothesis. Typically when we had a match between the two, we would have a one-tailed test. But here in this instance, we have a two-tailed test. The reason why we have a two-tailed test is because look at the inequality sign that we have with our alternative hypothesis. The inequality sign is not equal to, and that is the indicator that says we have a two-tailed test. So we have a match and we have a two-tailed test. Testing the claim. We've already evaluated the example with the linear correlation coefficient, so let's go ahead and use the true test statistic. If we were to calculate this old school, here's our formula. We plug in what we know, so 0.847 is our linear correlation coefficient. If we square that, we get 0.717, and we have a sample size of 10. So we plug these numbers into our formula, punch this out on our calculator, and we get 4.503. This is the true test statistic. Notice we get the same value from StatCrunch. So we can now evaluate the test by comparing our test statistic with our critical value. So here's the results window from StatCrunch. Notice we get the t-stat right here from our parameters table, 4.503. So we don't have to do the old school calculation if we don't want to. Looking here at our t-calculator, we can calculate two tails. So we're using the between option. And remember, when we use the between option, what's calculated here for the area is the area in between the tails. So because I have a 5% significance level, I want to put 95% here in my area for my probability calculation. And then remember, n minus 2 degrees of freedom. So degrees of freedom is 8, not 9. Then I press compute, and out comes my critical values, one on the left and one on the right. I have two critical values for a two-tailed hypothesis test. I can now reject H0 because the test statistic, 4.503, is right here inside the right tail. So it's in the right tail portion of my rejection region. So therefore, I'm going to reject the null hypothesis. And I conclude that there is sufficient evidence to support the claim of linear correlation between Shoeprint length and height. Supposing we had an instance of one-tailed hypothesis testing. This is where we have a claim that two variables have a positive linear correlation or a negative linear correlation. So if you have either positive or negative specified when it says test for correlation, you have a one-tailed hypothesis test. So you're going to write your hypotheses according to the table that you see here. If the claim is one of negative linear correlation, you have a left-tailed test, and you're going to select rho less than 0 for your alternative hypothesis. If you have a claim of positive linear correlation, you have a right-tailed test, and therefore the alternative hypothesis will be that rho is greater than 0. Notice that in every instance, the null hypothesis is always rho equals 0. So we can then, once we have set up the hypotheses, we can evaluate the hypothesis test using a linear correlation coefficient with the critical R-value table. We can use the p-value with a significance level, or we can use the true test statistic with the critical value from the t-distribution. So we have three different ways to resolve the test, but they'll all three come out the same. Let's look at an example problem involving the effect of clusters. So here we have a scatter plot at the right here on our screen that contains two clusters of measurements. So we've got 9 data points from women on the left and 9 data points from men on the right. Use the scatter plot to answer the following questions. So we have a list of 4 questions here. The first is, what is the linear correlation coefficient R for just the 9 data points from women? Second, what is the linear correlation coefficient R for just the 9 data points from men? Third, what is the linear correlation coefficient for all 18 data points? And 4, what do you conclude? Should the data be considered to contain 2 distinct populations, or should they be considered together? Let's look at these questions one at a time. So the first question asked about the data set for the women. So we weren't actually given a data set to dump into StatCrunch. So in that instance, what we need to do is look at our scatter plot and enter in the points ourselves. So here, this first data point here on the lower left is 1 on the x-axis and 3 on the y-axis. So I'm going to put 1 in for x and 3 in for y. So I'm going to do that with each of the 9 data points that you see listed here. Then once I have my data in StatCrunch, I can go to Stat, Regression, Simple Linear, and select my data and press Compute to get this wonderful results window. So now, looking at the results window, we have a linear correlation coefficient of 0. That means that there is no linear correlation for these data. The second question asks us about the subset of the sample that was taken from the men. I'm going to repeat the same procedure here that I did for the women. So I'm going to look at my scatter plot and take the x and y values for each of these data points and type them manually into StatCrunch. When you don't have a data set, that's the only way you're going to get your data. You have to take it visually from the graph. Then in StatCrunch, I'm going to go to Stat, Regression, Simple Linear, tell StatCrunch where to find my data, and press Compute. So now I get these results out, and notice here again the linear correlation coefficient R is 0. So notice how in each of these instances the data points formed a geometric shape that was symmetrical across both axes. So when you have this type of geometrical shape, notice that your R value will always be 0, because there's no one line of best fit that you can position that will actually fit the data better than any other. The third question we were asked said, put all 18 points together and come up with a linear correlation coefficient. So I can do that in StatCrunch. I'm not actually going to count each one of these data points one by one and select their x and y values. I'm just going to copy over the work I've already done into two columns that you see here, and then I'm just going to tell StatCrunch, go look at these 2 columns for your simple linear regression. Then in the results window, I find I have a linear correlation coefficient of 0.483. Much better than 0. So we've got a moderate amount of linear correlation here. It's not great, but it's not insignificant either. What do we conclude? Should the data be considered to contain 2 distinct populations, or should they be considered together? Well, considered separately, we had R values of 0. Considered together, we had a linear correlation of 0.483. So you might be thinking, that signifies that we should be considering each of these populations together. However, look at the scatter plot. There's 2 very distinct populations here. There's no real overlapping or mixing or melding of the 2 subsets of our population. There's a pretty distinct separation. The women are all over here, the men are all over there. So therefore, you don't want to put these 2 together. Trying to put them together and say there's a relationship between them by thinking that they're all one data set, that's going to lead you to some very misleading conclusions. So you want to consider each of these subsets as 2 distinct populations. Let's look at another example. We looked previously at lemons and car crashes. Or, no, actually, we didn't look at that previously. So let's look at it now then. So we have a table here listing weights of imported lemons in metric tons from Mexico. And it's compared with U.S. car crash fatality rates per 100,000 people. So lemon imports is there on the top, crash fatality rate there on the bottom. We're asked to answer the following questions. First, what does a scatter plot of the data look like? Second, what is the linear correlation coefficient? Third, what is the test statistic? Fourth, what is the p-value? 5, using a 5% significance level, is there sufficient evidence to conclude that there is a linear correlation between weights of imported lemons and car crash fatalities? And 6, do the results suggest that imported lemons cause car crash fatalities? Now, you might be thinking, before you even start working the problem, what possible relationship could there be between lemon imports and crash fatality rate? We're not going to see much here when we run the test. Well, let's just suspend judgment and let the numbers speak for themselves. So the first question we were asked was, what does a scatter plot of the data look like? And we're given these 4 options from which to select. So, again, dump the data into StatCrunch, look at Stat, Regression, Simple Linear. Then go to the second page there on your results window to get your scatter plot. Once you select your data columns and press Compute, of course. So when you get to that second page of the results window, by using the arrow at the bottom, you're going to see that answer option C is the one that we're looking for. Remember, you can always adjust the plot area and the axis values as needed to find your proper match. Sometimes that comes in very handy because the way that they actually present the plots there in your assignment window, it can be a little confusing sometimes. So if you need to make some adjustments to the graph you get in StatCrunch, by all means do so. Second question we were asked is, what is the linear correlation coefficient? Well, we already have that. We just go back to that first page of our results window and we just read it right off the results window. So here's our results window, first page. If we go to up at the top, there's our R value, 0.95896. Now, when you get an R value that's this close to 1, you know right off the bat that you're probably going to be pretty good. What is the test statistic? Well, the test statistic, again, take it from the parameter estimates table that's above the ANOVA table. Do not take your test statistic from ANOVA. So, in this case, negative 5.858. The p-value is listed right there next to the test statistic, 0.0099. And then the next question we were asked, using a 5% significance level, is there sufficient evidence to conclude that there is a linear correlation between weights of imported lemons and car crash fatalities? Well, we can use the critical R value to answer this question. So, going back, here's a cropped shot of our critical value table, and so we're going to find our critical R value here. Remember, we're using a 5% significance level, so we want this first column, and we have a sample size of 1, 2, 3, 4, 5 pairs. So that's going to give us a critical value of 0.878. We then compare this with our calculated value for R. Remember, which we saw on the previous slide, was 0.959. So since we're above the critical value for R, we do have linear correlation. We have sufficient evidence to conclude there is a linear correlation between lemon imports and car crash fatalities. If you're asked to provide critical values for R, remember you have 2, because you're comparing the absolute value of R with the critical value. So if you're asked for 2 critical values, you're going to go here to your table. One of them is a positive 0.878. The other will be a negative 0.878. Typically, these hypothesis tests are two-tailed, so you're going to have 2 critical values. Now, instead of comparing the test statistic with the critical value, we could compare our p-value with alpha. So back in the results window from StatCrunch, We had a p-value of 0.0099, which is less than our significance level. Therefore, the area represented by our p-value can fit inside the area represented by alpha. Therefore, we are inside the critical region. We reject H0. We do have sufficient evidence to support the claim of linear correlation. So either way you look at it, you get the same conclusion out of it. The last question we were asked was, do the results suggest that importing lemons causes car crash fatalities? Well, we had good linear correlation. We have sufficient evidence to support a conclusion of linear correlation. So, what do you think? Does importing lemons cause car crash fatalities? Well, I hope you didn't have to think long about it. I hope you said no, because correlation never implies causation. Correlation simply means there's some association, some relationship, but it doesn't follow that that relationship is one of cause and effect. So no, imported lemons do not cause car crash fatalities. However, look at our linear correlation coefficient. It's really good. I mean, 95%, that's excellent. So there is some strong association between our two variables. What do you think that could be? What might be the relationship between lemon imports and crash fatality rates? Well, if you think about this in terms of time, you can see that the seasons the rhythm of the seasons with these two variables are in sync. So, lemon imports go up when the growing season in the U.S. ends. So, that's generally when you get winter set on. So, in the winter, we're going to be importing more lemons than we would during the summer when we can grow a lot of our own lemons. So, lemon imports are going to go up in the winter and down in the summer. Similarly, we see the same pattern with car crash fatalities. Believe it or not, there are more car crash fatalities in the winter than there are in the summer. You would think with all the snow and ice on the roads that people would be more careful. Actually, it's the reverse. There's actually more, I just realized I misspoke. There's actually more car crash fatalities in the summer than there are in the winter. You would think with all the snow and ice on the road, you would have more fatalities in the winter. But people tend to be more careful with all the snow and ice on the road. And more careful driving tends to lead to less or fewer fatalities. In the summertime, when the roads are great, then you tend to see more people willing to push that envelope and be less cautious with their driving, and that leads to greater fatalities. So lemon imports are going to go down in the summer and up in the winter. Car crash fatalities are going to go up in the summer and down in the winter. So therefore, we do have a strong correlation between the two, and it's a negative correlation, because when one variable goes up, the other goes down. Look again at our critical R value table. Remember, we had this critical R value for 0.878. So we do have a linear correlation, meaning that there is some type of strong relationship there, and the strong relationship is explained by the seasons. That brings us to the end of this lecture. Again, if you have any questions, you know what you need to do. Otherwise, I will see you in class or the next video. Thanks for watching.